Hi everyone, and welcome to our video on the introduction to trigonometry of right triangles. So whenever we have a right triangle, anytime in trigonometry, let's just draw a right triangle given some angle theta, then we label it with these sides. So we say if this is where theta is, directly across is the opposite side. The longest side is always the hypotenuse. And then the side that touches the angle that's not the hypotenuse is the adjacent. So we always have those three keywords with any right triangle. Any right triangle, we always have that. And then we have this saying that can help us with trigonometry, SOH CAH TOA. So SOH CAH TOA is telling us if we have that right triangle, then sine of theta is equal to opposite over hypotenuse, and we usually abbreviate it there. So opposite over hypotenuse. And then the cosine part, cosine of theta equals adjacent over hypotenuse. And then the TOA part, tangent of theta is equal to opposite over adjacent. Okay, so along with this and the unit circle, these are kind of the two biggest things for being able to work with trigonometry. Okay, so sine theta, cosine theta, tangent theta, with right triangles, we always have SOH CAH TOA. The other thing we have with right triangles is Pythagorean's theorem. We'll abbreviate. With a right triangle, so there's a right triangle. Often we use A, B, and C. So a squared plus b squared equals c squared. However, if we're using it with the words, I kind of like to do that too. So we have opposite squared plus adjacent squared always equals the hypotenuse squared. Okay, in case they label the triangle strangely. Okay, so let's use this SOH CAH TOA with a given triangle to help us find exact values. So it says find the exact value of the 6 trigonometric ratios. So whenever it asks that, I usually just kind of set up a table. So sine of theta, so here's our theta in this problem. Let's mark it right there too. So sine of theta, cosine of theta equals something, and tangent of theta will equal something. And then let's get the reciprocals. Cosecant of theta will equal something. Secant of theta will equal something, and then cotangent of theta will equal something, which is just flipping our three answers to the left there. All right, so with our triangle, so they labeled it capital A, B, C. So usually they do angles as capital letters. They also might use Greek letters. Okay, so capital A, they might also use alpha. And then capital B, they might use beta. Okay, so they might do that, so or. And then capital C, they usually do like gamma or some other random letter. Okay, so they might use those other letters instead. Okay, so just in case. However, the main ones are usually the capital letters. Okay, however, and with those capital letters, I'm going to focus on the capital letters. We could label the triangle with our little letters. So big letters, capitalized letters are the angles. The lowercase letters are the sides based off the angle. So directly across capital A, we would say this is little a. Directly across capital C would be little c. And directly across capital B would be little b. And we can see, well, little b is unknown. Okay, so if we ever have a right triangle, so we often have this, we'll have two sides known, but a third side missing. Well, Pythagorean's theorem would help us with that. Okay, so in our Pythagorean theorem, again, we could do a squared plus b squared equals c squared to get it. Let's go ahead and do those with the letters this time. So we want to find b, and I'm just going to kind of, actually, let's not cloud it. I think that isn't needed. Okay, however, I could plug in what we currently have. So we have, here's where the letters, we have to be careful, actually. So let's rewrite it. Let's say opposite squared plus adjacent squared equals the hypotenuse squared. So the reason I want to rewrite it, so I changed my mind, is because sometimes so these letters are arbitrary. They might say that this is capital A. And then this wouldn't work the same way anymore. So we'd have to rearrange those letters. Okay, so we do have to be careful of that. So that's why, so I'm gonna erase that and just keep those letters. I am gonna label it in red, what we currently have based on this angle. So here's our angle theta. So I'm just highlighting it in red, making it a little bigger. Directly across from it is going to be the opposite side. Okay, and then we can see here's the 90-degree angle. Always directly across the 90-degree angle is the hypotenuse. Okay, so that should be the biggest side. And then little b, in this case, will be the adjacent. Okay, so that way I can double check to make sure I'm putting all the numbers in the correct spot in my Pythagorean theorem. Okay, so we have opposite is 24, so 24 squared, plus the adjacent, that's what we're trying to find. Let's use b, so b squared, equals the hypotenuse, which is 25 squared. Okay, and then we can square 24. That is 576. B squared is b squared, and then 25 squared is 625. So we need to get b squared by itself. We would subtract 576 on both sides. And we would get b squared, and do it all the way, b squared is 49. And so we can square root both sides now. Remember, when you square root, you should include plus minus. However, on this problem, it's a triangle. We should only have positive lengths. So we would get b is positive, 7. So the square root of 49 is 7. Okay, so we have b is 7. Okay, and so that was our first step. So our first step is to use Pythagorean theorem if we have a missing side. Now that we've got all three sides, we can now do SOH CAH TOA. And before we actually move on with SOH CAH TOA, so I have this table here called Pythagorean triples. So there's special right triangles like the 3, 4, 5 right triangle. So the first two numbers are a leg in all of them. So a leg, and then the 5 is the hypotenuse. Okay, so it's like the A, B, and C of a right triangle. And so what this is stating is if you have two of the numbers and you notice the pattern, you can get the third without actually doing the full theorem. So notice this right there was our case. So 7 is one of the legs, 24 is one of the legs, and 25 is the hypotenuse. Okay, so these are kind of common, so they can speed up that step number 1. However, not all right triangles are these special triples, and it's not that big of a deal to do these few steps anyway. Okay, but just in case, those can speed it up if you do catch one of the special cases. I would say this first row is a good one to know, and then probably like this one and this one. After that, the numbers get kind of big and strange, and those aren't as common. So these first 5, they use quite a bit. Okay, anyway, so back to this problem. We have SOH CAH TOA. As a reminder, that means sine of theta equals opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And then tangent of theta is opposite over adjacent. So sine of theta, so we already have those labeled. Opposite we can see is 24. Over the hypotenuse we can see is 25. That's it. So sine of theta is equal to 24 over 25 in this right triangle. Cosine of theta, adjacent we already have labeled, it's 7. Over hypotenuse, 25. Done. Tangent of theta we also already have labeled. Opposite is 24. Adjacent is 7. Opposite over adjacent, done. And then now that we have those 3, we have the other 3. Cosecant of theta flips the sine theta answer, is 25 over 24. Secant of theta is 25 over 7. And then cotangent of theta would be 7 over 24. So how nice. Okay, so that's how we use these. So any right triangle we can now do SOH CAH TOA to, and or Pythagorean's theorem. And that is this whole section. So if a bunch of other videos are coming, but the main idea is always SOH CAH TOA. Okay, so let's take a pause. Thank you for watching. If you have questions, please let me know.